Okay, so for our next set of slides, what I'm going to talk about is another model known as the Gaussian process. Okay, so we've seen Gaussian again for a lot of things. We're going to see it for one more thing, the Gaussian process. And the Gaussian process is very interesting because we're going to see that it does correspond to doing Bayesian linear regression when we use kernels. So now we've seen the benefit of kernels, so it allows us to essentially compute dot products without having to go to the new space that might be high dimensional, so we can do this quickly. But now let's apply this in the context of some generalized linear model, and the first one we're going to consider is Bayesian linear regression, and we'll see that whenever we use kernels in that context, it leads to what is known as a Gaussian process. Okay, so that's the first part. But then there's something also very interesting about Gaussian processes. They turn out to be equivalent to a neural network that has one hidden layer that is infinitely large. Okay, so there's this nice connection between these classic techniques that we've seen, in particular Bayesian linear regression, that we are now going to call a Gaussian process. So that happens to be equivalent to doing Bayesian learning in a neural network with one hidden layer, whenever you've got a hidden layer that is infinitely long. Okay, so to first illustrate what is a Gaussian process and how it works, I'm going to draw a picture, and then we're going to delve into the details of how it's constructed. Okay, so again, we're interested in doing regression, and now I've got some data. So my input is x, my output is y, and let's say that the function that I'd like to discover is this function. Okay, so this is my true underlying function, f of x. Okay, so I have some data. And let's say my data is here, here, and here. So in this case, just to keep things simple, I'm going to assume that the data I observe, there's no noise in the measurement. So I have a corresponding x, and then the y that I measure is not perturbed by any noise. So therefore, the data point that I observe is exactly where the function goes. Okay. So now with if we were trying to do linear regression with this, we obviously could not find this function because we would find a function that is linear and goes near those points. But we'd like to instead come up with something that is nonlinear. Now, if we consider Bayesian linear regression, and we have to, let's say, specify some basis functions ahead of time, then we could consider a set of basis functions that would allow us to span a space of functions that would have a certain parametric form. But here, there's no guarantee that this function would have any specific parametric form. So ideally, I'd like to have a model that is flexible and allows me to capture any function that happens to be going through those points. And this is where the Gaussian process is going to be quite nice, because we'll see that it does not assume any parametric form for the underlying function. As we get more and more data, it's going to be flexible enough to capture essentially any function that goes through those data points. And here, even though I've assumed so far that those data points, there's no noise in their measurement, we can also consider noise in the measurements. But just to keep things simple for now, I'm going to assume that there's no noise in the measurement. Now, what the Gaussian process is going to do is to essentially learn a distribution over what is the outcome of that function at any point. So those points, I observe them. There's no uncertainty. I know the function must go through here if I assume that there's no noise in my measurement. But then anywhere in between two observed data points, I don't know where the function should really be going. So what the Gaussian process is going to do is to essentially model this uncertainty with a distribution. And then what I'm going to do now is just draw plus and minus 1 standard deviation that would correspond to some uncertainty around where the function might go. Okay, so here, this dotted line is going to correspond to minus 1 standard deviation, and then this other dotted line here is plus 1 standard deviation. So the idea is that the Gaussian process is going to correspond to a distribution over the outcome of the function at any point along the x-axis, right? Because the function is applied to x. There's a corresponding y that should come out of f of x, right? And I don't know where that y should be because I mean, that's what I'm trying to learn. And then it's going to express this uncertainty by a distribution. And here the intuition is that if I have a point here, x, and I want to know what should be the y, then the Gaussian process is essentially representing a distribution that is Gaussian over where the line might go at that point x. And then it's doing this for every point x. So if I consider another x, it's essentially saying that there's a Gaussian distribution that corresponds to where the line should pass by. Any questions regarding this? Yeah?
So your variance is the distance from another data point?
Sorry, say that again?
The variance of the point distribution is the distance from the data point?
So the standard deviation that I've got here, it corresponds to essentially the distance. So I guess, yeah, I think that I've got some distribution that comes out of the board, right? So the probability of the output y being in any specific location would be given by a distribution that comes out of the board. And now what I'm really doing is drawing contour lines that correspond to where I've got plus and minus 1 standard deviation for that distribution. And then obviously the further apart is the dotted line from the function. That means the more uncertainty I've got. So it means that my Gaussian distribution is flatter, it's wider. Okay. All right, so now we're going to discuss how we can construct such a distribution. And then the beauty is that with this, we're going to be able to learn distributions over functions so that we can effectively do regression without limiting ourselves to a specific parametric form. So the Gaussian process is in fact a non-parametric model because we're not restricting ourselves to a specific parametric form. Okay, so in Bayesian, if we go back to Bayesian linear regression, so if we go back to Bayesian linear regression, if you recall, when we work with Bayesian linear regression, we assume that the function f was essentially given by a linear expression of w transpose phi of x, where the output f was perturbed by some noise epsilon. Okay, so now I'm going back to allowing noise. And here we just assume that, okay, what we are missing, what we don't know is w. And then when we do Bayesian learning, what we don't know, we express a prior about this. and then when we see some data, then we revise that distribution, and that's how we learn. Right? So here we start with a prior distribution probability of W, and then we computed a posterior distribution that was then dependent on the data that came from the multiplication of the prior by the likelihood. And when we worked with Gaussians, when we made everything a Gaussian, so for instance, when the prior is Gaussian, the likelihood is Gaussian, and the posterior is also Gaussian. So everything was beautiful in that sense. Okay, so this is just a recap of Bayesian linear regression. And when we discussed that, this was when we focus on weights, because the weights were the unknown, and I'm going to call that the weight space view. But now we could have a different view that I'm going to call the function space view. And now the idea is that instead of thinking of W as the unknown, really the thing we're trying to estimate that we don't know is the function itself, f. Obviously, the function depends on some parameters W. That's what we don't know. But that's one way of viewing things. Another way is just to say, well, let's treat f as the unknown and work with that. And then we'll have a formulation in terms of the function space. OK, so here you see same setting as before. The only difference is how we view things. So here we're going to treat f as the unknown. And now this gives us a function space view. So if we're doing Bayesian linear regression in a function space view, we're going to start with a prior over functions and then compute a posterior. Now to express a prior over functions, what we can do is simply expand the fact that our function really comes from W transpose phi of x. And then so we have a prior instead of over the weights. And now, given the weight, we know what the function is going to be. So it's W transpose phi of x. So we can write this as a deterministic distribution, take the integral with respect to W, and this will give us a distribution over f. Okay? So here, what I've done is simply express a distribution over the function with in terms of the distribution over W when a function depends on W. Okay? So here this is really the marginal in terms of W, a conditional of f given W, and then when I integrate W, then I get a marginal in terms of f. And then this distribution here is deterministic because if I know W is given, then I know what f is, and there's no uncertainty. So that means that my distribution would be 1 for the corresponding f, and 0 for any f that is not the right one given W. Okay? But generally speaking, that's how we can write it. So this gives me a prior. And now, if this is a Gaussian, this is deterministic. When I take the integral, I'm going to get a Gaussian again. Now I can do the same thing with the posterior. Earlier we saw how we can obtain a posterior for W. But now if we want to express a posterior with respect to f, we can multiply by the property of f given W, take the integral, and then we'll get a posterior that is with respect to the data. And same thing, this is Gaussian times the deterministic, take the integral, you get a Gaussian again. Any questions regarding this? Good? Okay. All right, so now when we talk about Gaussian processes, the idea is that we're going to do Bayesian linear regression with respect to the function space. And then in a function space view, what happens is that we end up with a Gaussian at every f of x. Okay, so the function is unknown, and now we want to express a distribution over the function. But then really the function, its purpose is to be applied to some input x, so I can verify when I apply f at x what the output should be, and then express a distribution over that output. Right? And then I can do this for every x, and that's essentially what I have on the board here. Okay, so what I've expressed here is a Gaussian process where for any x, there's an output, and now I don't know where that output should be according to the function, so I'm going to express a Gaussian distribution with respect to the location of that output for every possible x. And what I've done here is just show you plus and minus 1 standard deviation for every location. Okay, so implicitly then this gives me a distribution over the function. And then naturally, when I observe a point, and if there's no noise in the measurement, then I know the function must go through here, so then there's no uncertainty, and that's why the two curves for plus and minus 1 standard deviation, they intersect at, or they meet at the line, so that means there's no uncertainty, I know where the function is there. Okay? But everywhere else, right, there's a little Gaussian, essentially, that indicates the uncertainty. Okay, so now those Gaussians, we can obtain them by considering the fact that f itself is really dependent on w. So really we have Gaussians that are correlated through w. So we have a Gaussian for the output of the function f at every input x. So there's a separate Gaussian for each one of them. But then all of those Gaussians, they're correlated together. And this correlation is going to lead to a kernel. And that's where the connection is with kernel methods that we've talked about so far. Okay, so again, if I go back to the board, you see, if I observe a point, and I know the function must go through this point, now because all of the Gaussian distributions for all of the outputs are correlated, it is natural that you see, I've observed this point. Now if I consider another point that is arbitrarily close to the one that I've observed, right, then I would expect that there's very little uncertainty here, and it corresponds to this idea that if I condition on the value for a given point, then another point that is really nearby is going to have an output that should be also nearby, and therefore I'm going to have little uncertainty. So that's why here you see my two curves for plus and minus 1 standard deviation, right? Then they essentially are meeting and then gradually go away because the uncertainty increases, but then I do expect that it's going to be a curve and it's not going to be discontinuous, right? So I expect the curve to essentially have values that are close to what I've observed. Okay? And that is determined by the correlations that come from the covariance function that I'm going to define. Okay? So effectively, a Gaussian process is an infinite number of Gaussian distributions that are all correlated together. And then if you have an infinite number of univariate Gaussian distributions that are all correlated, it really corresponds to an infinite multivariate Gaussian. Okay, so a multivariate Gaussian is really multiple univariate Gaussians that are correlated together. And if you have an infinite number of them, then this is what we call a Gaussian process. Okay, so that's what we've got here on the slide. Gaussian process, infinite dimensional Gaussian distribution. Okay, so now how do we represent mathematically a Gaussian process? We do it in the same way as a regular Gaussian distribution, in the sense that I'm going to specify a mean and a covariance. But now, because I need to do this for an infinite number of dimensions, then I can't just write down a vector. I'm going to have to write an infinite vector, and that really corresponds to a function itself. So here, the mean is a function, and now the covariance, which should be a covariance matrix, is instead going to be a two-dimensional covariance function so that I can capture an infinite number of dimensions. Okay? Now, these functions take as input x and x prime, in part because you see the function f takes as input x. Therefore, the mean function should also take as input x. And then the covariance function should take as input two things, so x and x prime. Okay, so m of x is our mean function, so it's the expectation of f of x. And then k of x, x prime is a covariance function, so it's the expectation of f minus m times f applied at x prime minus m applied at x prime. Okay? All right, with this defined, now we can figure out what is the corresponding mean function in the function space view that would correspond to the mean whenever we worked in the weight space view. So in the weight space view, you see we started with a prior over weights that was essentially a Gaussian of mean 0 with some variance, here 1 over alpha for every weight. Now if we start with this in the weight space view, then in the function space view, the mean is the expectation. Now I can expand this where f is just w transpose phi. So then the expectation will apply to w. And the expectation of w is just 0. So it means that my mean function is just the 0 function. I can do the same computation for the covariance function. So here, the covariance function by definition is the expectation of f minus m times f minus m. But since m, the mean function, is 0, I can drop this, and now we're left with the expectation of f times f. So that's what I've got on this slide here. So the expectation of f times f. If I expand this by replacing f by phi transpose w, then I get this expression. And now the expectation of w transpose, that corresponds to the covariance of my prior with respect to w. And we said that this was 1 over alpha times the identity matrix. I can drop the identity matrix since it doesn't change anything. And then I can rewrite this as follows. So that's essentially the covariance function. Okay, so this is just a little bit of math to illustrate how we go from the weight space view to the function space view. But now let's just see with some picture what kind of functions we could sample from a prior that's defined by a Gaussian process. So here I've got two pictures. The first one illustrates the type of functions we could sample from a Gaussian process that has a kernel function that uses the Gaussian kernel. Okay, so here let's not get mixed up. Okay, we've got Gaussian process, which is a distribution. It's an infinite dimensional Gaussian distribution. And then we have a covariance function that is essentially the Gaussian kernel, but that's not a distribution, right? It's just the algebraic form that's used for this particular covariance function. Okay, we don't have to consider Gaussian kernels. We can also consider exponential kernels. And here I'm showing you some curves that are sampled from these distributions. And then depending on what kernel we use, the curves will have different properties. So if we use the Gaussian kernel, the idea is that the curves are going to be fairly smooth. And that has to do with the fact that, you see, the kernel encodes the covariance. And here you see if I have a large positive covariance, it means that whenever x increases, then x prime should increase as well. And as a result, if I'm looking at my unknown curve, and then I observe one point, if I have high covariance, then the next point that's arbitrarily close is going to be pretty much at the same location and might just vary a little bit. But if I have a low correlation, then it could vary quite a bit. And that's essentially what is shown with the exponential kernel here. So this one has a lower covariance in general. And then you see there's a lot more variability, so the curves are not as smooth. Okay, so here we can see that the Gaussian kernel, because of the exponential, is always positive. So that means we've got positive correlations. So that helps with ensuring that we're going to have values that are roughly the same. But then the higher this is, and here because we square the distance. So in other words, if I've got an x and an x prime that are really close, and then I square this will make the covariance higher. Whereas the exponential kernel, here we don't square the distance, we just take the distance, absolute value. So then the covariance is not going to be as high, and then there's more variability. And that's how we end up with these types of curves. So in other words, you see the kernel has an important impact on the type of curves that we consider. And then so it's important to actually choose a good kernel. Okay, any questions regarding those pictures? Okay, all right, let's continue. Okay, so now let's go ahead and see how we can do regression with a Gaussian process. So here, regression with a Gaussian process does correspond to doing essentially Bayesian linear regression with a kernel. So if we do Bayesian linear regression in the weight space view, then the goal is to compute the posterior, which is a property of W given the data. And then we saw a few lectures ago that when we did that, the complexity would be cubic in the dimensionality of our data. Okay? And then if we work with a mapping phi, right, then it's going to be cubic in the dimensionality of the number of basis functions. Actually, so it's going to be cubic simply in the number of basis functions. But when we work with a Gaussian process, instead, what happens is that we are working in the function space view. We express our distribution directly on f, which for some people might be more intuitive, and for some other people it might be less intuitive. It depends whether you're more comfortable with weights or thinking directly in terms of the function. But the beauty is that the complexity now is independent of the dimensionality, so it doesn't matter how many basis functions we use. Instead, it's going to be cubic in a number of training points in the amount of data. Okay? So for instance, if I use a Gaussian kernel, which has infinite number of features, therefore infinite dimension, I cannot use this for Bayesian linear regression in a weight space view, but I can use it in the function space view because now the complexity is independent of the number of basis functions. So instead, it depends only on the amount of data. Now, if I'm in a big data regime, though, I must admit that the Gaussian process does not scale because now you would need complexity that would be cubic in the amount of data, and then we've got a problem. So those two views have their pros and cons. Okay, so as a quick recap, when we did Bayesian linear regression, we started with a prior. We have a likelihood that is a Gaussian expressed in this form. And then we saw how we can compute the posterior, which has a mean W and then a covariance A inverse that are expressed in this form. And then we also saw that we can do prediction. So in other words, given a new point x star, if I want to compute a prediction for the output y star, then it will have a Gaussian distribution that has this form. Okay, so when we did this, then the complexity for the computation had to do with computing the inverse of A, and that is cubic in the number of basis functions. Now, with a Gaussian process, we can do the same thing, but in a function space view. So here, I start with a distribution with respect to f. So it is a Gaussian. As we discussed earlier, it would have a zero mean and then a kernel that would be the one that we just saw a few slides ago. And here I'm using some notation where, since I want to emphasize that these things are functions, right? So I'm going to write f dot to mean that it's a function that takes an input. When I write f of x, then it makes it clear that I'm looking at the output of that function at a specific x. But if I want to allow x to vary and be anything, then I don't want to specify x, and instead I'm going to use this notation where I replace x by a dot, meaning that it's a function, and I haven't defined yet what I'm applying it to. Okay? So, yeah, so then from that perspective, right, you see we've got a distribution over functions, and then it's a Gaussian process that has a mean function and then a kernel function like this. There's a likelihood function that is also Gaussian, and then I can compute the posterior that will have a mean function and also a revised kernel function that have the following forms. Okay, so I'm skipping the math for this. I'm sparing you guys the details. But in any case, that's what it would look like if you do the derivation step by step, and then you can also compute the prediction. And then the complexity of doing all this is going to be essentially cubic in this matrix k plus sigma square I. So that's essentially our kernel matrix at all the pairs of data points. So it's going to be cubic in this, so that's why it's cubic in a number of training points. Okay, any questions regarding this? Okay, so the good news is that you guys will get to practice this in assignment 3. So you'll get to compare what happens with linear regression and also Gaussian processes. Now, let me mention that what is interesting in terms of Gaussian processes beyond just the view of linear regression is the fact that there is this nice correspondence with an infinite neural network. So here, this is a classic result where back in 1994 it was shown that if we take an infinite single hidden layer neural network, then the limit of that is actually a Gaussian process. So it's very tempting often to make our neural networks arbitrarily large. And today, I guess we want to make them deep as well. But back in the 90s, we knew that if we could just make it very wide, then it could be quite expressive. And we knew that in the limit, it could approximate any function. But we didn't actually have a way of doing this in practice. And if you want to actually work with an infinite neural network, then you're effectively working with a Gaussian process. Okay, so yeah, I've got a few more slides that explain this, but I'll cover them next lecture. So let's stop here. Next lecture, we'll go through the proof for this. And then I've got as well an example in robotics where this gets used. Okay, so here, to show this connection, the idea is that we're going to treat our neural network as a function. The idea is that when we optimize a neural network, right, we're essentially doing some form of regression if really we're fitting continuous data, right? So we're doing some form of regression, and then the neural network is encoding a function. So if it's a two-layer neural network that has a first layer with an activation function h, and then a second layer that has no activation function, or if you prefer just the identity activation function, then this would be its algebraic form, right? So this is what the mathematical formula of the function that corresponds to this type of neural net looks like. And now we have some data, and what we're hoping is that our neural network is going to fit this data well. And now this is actually a Patrick form, right? So if we want to make sure that we can fit any function arbitrarily closely, then we need to make sure that we are considering an infinite number of hidden neurons. That means here that the sum with respect to j is going to be infinite. Okay? All right, so with this in mind, if we now do Bayesian learning and we consider the weight space view, so in this neural network, our unknowns are the weights, wkj, wji, wj0, wk0. And the idea is that we would like to express an initial belief with respect to those weights. If I start with a prior over wkj that has a mean 0 and a variance that's alpha divided by j, and then for wk0 also a mean 0 and then a variance that's sigma square, then I will be able to show that the posterior is a Gaussian process that has this form. And here a Gaussian process, again, is really just an infinite dimensional distribution that is Gaussian with a mean 0 and then this covariance function. Okay, so yeah, so that's what I'm going to start with in the weight space view. Now, it will be useful for us to work in the function space view here. So in the function space view, whenever I have a number of hidden units that goes to infinity, then I can use the central limit theorem to verify that the output is going to have some noise that follows a Gaussian distribution. And here the idea is that the central limit theorem essentially says that if I have an infinite sum of identically and independently distributed variables, then the resulting sum is itself Gaussian. Okay? So now if I look at my expression here, so this is how I defined my two-layer neural network. I have a sum. Whenever my number of hidden units goes to infinity, this sum becomes infinite. And what we're really doing, you see, is taking a sum of random variables, wkj, times here's some other component that is also dependent on some random variable, so that's also random, and then plus another random variable. So in any case, there's a sum of terms here, and then this sum is infinite, right? And it's really a sum of terms that are all random, but they're all distributed in the same way, because here they all consist of a weight multiplied by some expression here plus another weight. And then if all my weights, I assume that my prior distribution is independent, then you can verify that these expressions, so these terms, are all going to be independent. So they're going to have the same distribution, but they're all going to be independent. And that's all we need to apply the central limit theorem. Okay, so here, yeah, the central limit theorem basically says that I've got a sum of random variables that correspond to these expressions. Here it doesn't matter what their distribution is. As long as this sum is infinitely large, the sum itself is going to be Gaussian. And therefore, I know that the output of my neural network is going to be distributed according to a Gaussian. And now what I'm going to show you on the next two slides is how this Gaussian has a mean 0 and a covariance function that's equal to this expression. Okay, so let's derive the mean. For this, all I have to do is simply look at the expectation of the output of the neural network. Right? So again, we're computing a distribution over the output of the neural network. So essentially here we're making a prediction about what the output of the neural network is going to be for an input x. And here, if we're doing Bayesian learning, we're going to have a posterior distribution. This posterior is Gaussian. So then the distribution over the output is Gaussian too. And now we need to verify that the expectation, which is the mean, is 0. So this slide shows that if I replace f by the expression that I have, So here, f of x is essentially wkj times h of some expression plus wk0. So I obtain here wkj, h of some expression. So actually here, I guess I should change the notation. So strictly speaking, this is not x. This is really sum of I, wj, I, xi plus wj0. So I should replace that so it's not exactly x. But in any case, it's a function, h of that expression, and then plus wk0. Now, expectation of a sum is the same as the sum of the expectation. So that's why I have an expectation here and expectation here. And then since wkj is independent of h of x, right? So the weights that appear in h are different from wkj. And all the weights, I'm going to assume that they're independent. So then I can change this expectation to a product of expectation. And finally, since I assume that the expectation of each weight alone is 0, then I can just write down 0, and then this whole expression boils down to 0. Right? So we assume that the expectation of those weights were 0, and that's why we can do this substitution here. Okay, any questions regarding this derivation for the mean? Okay, very good. We can do a similar derivation now for the covariance function. So the covariance function, by definition, is the expectation of f of x times f of x prime minus the expectation, or minus the product of the expectation of f of x by f of x prime. So now I can expand this. The second term, we've just seen how the expectation of f of x is 0. So this term disappears. So we're just left with the first term. And now I can replace f by its definition. Then I can push the expectation inside the summation. Then I can separate the terms that are independent so that I have a product of expectation. After that, I can notice that the expectation of w square is in fact equal to the variance, because normally the variance is the expectation of x squared minus the square of the expectation of x, but the expectation of x is 0, so that's why the expectation of the square is equal to the variance, so I can replace that by the variance. And then I assumed initially that my variance was alpha divided by j, and here sigma square, so I just substitute this in. And then the sum with respect to all the j's will essentially cancel this capital J here, and I'm left with this expression. Okay, so yeah, so this is a derivation that okay, has quite a few lines, but still should not be too difficult. And then it confirms what we had on the previous slide here. Okay, so it confirms this expression for the variance. Any questions regarding this? Yeah?
Can you go 2 slides forward?
2 slides forward, okay.
On the third line you have 2 sums, and on the fourth line you have 1 sum. What happens to the double sum? Oh.
Right, so yeah, I've got 2 sums here. What happens is that yeah, when we push the expectation in, some of these things simplify. Well, okay, so I guess what I would do is take this sum times this sum. So this will give me this expression here. And then the cross terms, this sum times wk0, since the expectation of wk0, 0, this disappears, right? And then we're simply left with wk0 times wk0, which gives us this. So essentially only the terms only whenever it's a weight multiplied by itself, that then the expectation does not vanish. If I have the expectation of one weight times the expectation of another weight, the terms vanish because expectation of a weight is 0. And that's how the two summations will essentially boil down to a single summation after that. Okay. Any other questions? Okay. And perhaps, yeah, one thing that's interesting to note is that here, when I assume the following variance, right? So this was so that when I do this derivation, I arrive at this expression. And in particular, it was important that I assume here that the variance is alpha divided by j, so that when I do the summation with respect to j, then this cancels off. So this was just out of convenience. And that was the main reason why I chose those variances. But this is a prior, so for the prior we can choose anything we want. Okay. All right, so in summary, you see what we've just shown is that if we have a neural network, 2 layers, and here it doesn't matter what is the activation function h for the hidden layer, so it can be anything, right? And as long as I'm doing Bayesian learning, where I assume that my prior over the weights has mean 0, and all those priors are independent, right, and identically distributed, then I will end up, well, then I will be able to apply the central limit theorem. So therefore, my sum of terms that's infinite is going to lead to a sum of random variables that is infinite, and then that sum itself is going to become, is going to have a Gaussian distribution. And that's how it becomes a Gaussian process. Now, when we say it's a Gaussian process, it should have a mean and a variance, right? And that's what we computed. So it has mean 0, and it has this variance here. Okay, so let's talk now about an interesting application, because we've done a fair bit of math. And you might be wondering, you know, where do we use this in practice? Is this just theory, or do people actually use that? It turns out that Gaussian processes are quite useful, have been quite popular in robotics for a number of years. And in fact, roughly 10 to 15 years ago, Sony released an important robotic platform called the Aibo robot. So it's a dog, it's a robotic dog. And then it has different joints, and the idea is that it can walk. Now, this type of robotic dog became popular not just because it's cute, but also because there's an important competition that's been running for more than 20 years, known as RoboCup. So it's a competition where robots play soccer. And then researchers around the world have been participating in this competition. And then for a number of years, this was roughly 10 to 15 years ago, this platform, these types of robots were essentially the type of hardware that was used in that competition. So the idea is that there's 2 teams. Each team has a number of robotic dogs, and then there's a ball, and then they play soccer with this ball. And now the question is, for each team, can we optimize the parameters of those robotic dogs so that they can play well? Okay, so just to illustrate, let me show you a video. Okay, so what you're looking at is a soccer field, and we've got some of those robotic dogs. I guess they're just waiting for the ball. They're actually looking for the ball. And I guess the ref is going to come and put the ball in the middle. Here we go. Okay, and now they can start playing. So there's another team over there. And yeah, it's just like regular soccer, right? So they can walk around, they can kick the ball, they can pass it to other players. And the idea is that they play a match, and then their goal is to score as often as possible. Now, you can imagine that programming these types of robotic dogs is not obvious. Okay, so here, interestingly, in the early days, I guess the bottleneck was not so much how do you get a team of robotic dogs to play well together, but was really just how can you get one robotic dog to walk properly, and in fact to walk or run as fast as possible. Because if you have a robotic dog that can go faster than the other dogs on the field, then it can reach the ball, and then your team is going to have a major advantage because it can always reach the ball faster than the other team. So here, yeah, getting those robotic dogs to walk properly and to walk fast was something that researchers ended up working on for a number of years in order to perfect the gait and reach a point where it was as good as it could be. And then after that, it was more team strategy that mattered. Okay, so this will keep on going for a little while, so let me stop it here. You can watch a lot of those videos on YouTube if you want. Okay, so with these robotic dogs, there's an important gait optimization problem. And here what I mean by gait is essentially the ability to walk. So the problem is that we want to find the best parameter setting of the gait controller to maximize the walking speed. And again, in robotic soccer, right, a very simple skill that every robotic dog needs to master is the ability to walk, and in fact to walk as quickly as possible or to run as quickly as possible to reach the ball before the opponent, right? So then that's very important. And the problem is that when Sony started developing this hardware platform, in the early days, there wasn't good software that came with it. And then so the researchers had to essentially design controllers to get the dogs to walk. So imagine that you see the dogs, they have several joints that correspond to ankles, knees, and hips for each leg, right? And now there's an actuator for each one of those joints. And now I guess controlling these things is not obvious. So here you really have to develop some careful optimization to set the parameters in a good way if you want to obtain even just something that corresponds to a walk and then ultimately a fast walk. Okay, so there are many solutions to this problem. At the end of the day, we can think of it as a search problem in the space of parameters of controllers. But one technique that stood out early on were Gaussian processes. And still today, Gaussian processes are quite important in robotics. Okay, so in this problem, there are 15 parameters that determine the gait of a robotic dog. And then setting those 15 parameters will influence, again, the speed or even the ability to walk. So now the question is, can we find the best setting? And here we want to find a setting that maximizes the speed. So there is an implicit underlying function f that takes as input a setting of the parameters and outputs a speed. And now we'd like to, I guess, discover what is that function. And more than that, find which x maximizes this function. Okay, so yeah, so from an optimization perspective, we could say, well, it's just maximizing the function f, but the problem is that we don't have the function f, right? So here, it's not clear how setting the parameters of the controller will lead to a gait of a certain speed, right? So changing the parameters changes the speed, so this function is unknown, and we also have to discover it. So it's not a pure optimization problem. It's in fact more of a machine learning problem because we don't know the function f. Okay, so let me draw a picture to illustrate how we can use a Gaussian process now to learn this function, and more than that, learn it in a way that will allow us to find out quickly what is the maximum of that function. In other words, the setting of the parameters that maximizes the speed. Okay, so the problem is that, you see, we've got possible settings of the parameters that corresponds to the x-axis. And then there's the speed for each setting that corresponds to the y-axis. Okay, so now we're going to learn a Gaussian process. And what I'm going to do is draw a curve that corresponds to the mean of this Gaussian process, and then some additional dotted lines that corresponds to plus and minus 1 standard deviation. Okay, so let's say that this is the mean of my Gaussian process, so that means m of x. And let's say that I've observed some data points that are here. Okay, and now this dotted line corresponds to minus 1 standard deviation, and this one plus 1 standard deviation. So again, the idea is that the Gaussian process allows us to express a distribution over this unknown underlying function f that returns the speed for any setting of the parameters. And now let's say that I've already observed what is the speed for some settings, and this corresponds to those x's here. This corresponds to those points. Okay, so those points are observed. I've already observed what is the speed. Okay, so then I don't have any uncertainty, but then for the rest, I still have some uncertainty. And you can think of those dotted lines as essentially contour lines of my Gaussian process, corresponding to plus and minus 1 standard deviation. Okay, so if this is my Gaussian process at a certain point in time, what I'd like to do is to carry out more experiments to observe more data. And what I mean by carrying out an experiment is that the way we can get a data point in this problem is by carrying out an experiment where, let's say I draw a starting line, and then I put my robotic dog behind that starting line, and then I draw another finish line, perhaps 10 meters away, and then I get the robot to start, and then I time it, and then I verify how much time it takes it to reach the finish line. And then based on this, I can infer what was the average speed of the robot, and then carrying out such an experiment now tells me for given x, so setting of the parameters, what is the output y, which is the speed, and then it corresponds to a data point like these. Okay, so now you can imagine that in this problem, we are not going to have a lot of data, because carrying out such an experiment means that you have, to set up something on the floor with a finish and a start line. You have to put your robot behind the start line. You have to press a button so it gets going. Then you wait maybe a few seconds to a few minutes before it reaches the finish line. And then you record that, and then you repeat. Right? So we're not in a big data regime here. We're in fact in a very small data regime. Okay, so doing this, researchers, they could get maybe on the order of hundreds of points that would correspond to hundreds of trials, but not much more than that. Right? So this is part of the problem here, and this is why a Gaussian process was okay, because here the complexity scales with respect to the amount of data. We know we're never going to have a lot of data because it is expensive to carry out each experiment. But then at the same time, we don't know what is the parametric form of the function, so it makes sense that we would work in the function space view, and then we can express a Gaussian process that can fit an arbitrary function wherever it happens to be. But now more than that, we don't want to actually find what the function is, but instead find what is the maximum of that function, because this will give us the best setting of the parameters to maximize the speed. So if we already have 4 data points, because we did 4 of those trials, now an interesting question is, what should be the next experiment that we do? In other words, we put the robot behind the starting line, and now what setting of the parameters, so what x should we pick for the next experiment? And if you look at this curve, right, maybe a simple heuristic could just be, well, let's try the setting x that looks most promising according to our Gaussian process. And here, most promising, there's many ways to resolve that, but intuitively, you see wherever we have a high mean and perhaps a high variance, right, could be a most promising point. And here maybe I'll simply choose this point because it has perhaps, I guess, yeah, it looks promising. And even if it turns out that it's not so good, I will resolve a lot of uncertainty because there is a lot of space between the mean and plus and minus 1 standard deviation. Okay, so here I'm going to call this x new. So this will be the next data point that I will observe. Okay, so I carry out the experiment, and I observe the value. And let's say the value happens to be here. Okay, so now I need to revise my Gaussian process to take into account this data point. So I'm going to draw another curve here that corresponds to the updated curve. Okay, so should be like this. Okay, so you see this new data point corresponds to this one. Now the main difference is that my mean function goes through that data point. Now here I'm trying to draw this roughly the same, right? So I mean, though the curve, at least the data point should be exactly at the same spot, but I mean my drawings are not perfect. In any case, you get the idea. And now you see the curve has come down. So it now goes through the new data point that we got. Okay? And now the next step, we're going to do the same thing. Perhaps look for a most promising data point. And intuitively, right, it would make sense to perhaps consider this data point because there's hope that maybe this is going to lead to a very fast walk. And let's say that we observe instead the point here. So then the curve is going to be revised. And so this is now the x new. And I'll have another curve. Okay, so it will look like this. Okay, so now I've added this data point here where my curve has come down again. Okay, and the process would keep on going like this. At every step, I would simply choose a point that is promising, perhaps something that has a lot of uncertainty, and also something that has a high mean that looks promising. Any questions regarding those pictures? Okay, let's continue. All right, so to summarize, the algorithm starts by initializing a Gaussian process, and then at every step in this loop, we're going to select a new x. This is a new setting of the parameters where we carry out an experiment. It corresponds to a new data point for the curve. And the heuristic that was used in that work was essentially to maximize this expression. And the intuition here is that we are maximizing the variance. So here, k of x corresponds to the variance. So we're looking for a point where there's a lot of variance or a lot of uncertainty. And then divided by the negative of the mean at x. So here, this also has the effect of selecting points with a high mean, right? Because when you divide by the negative of the mean, then you're essentially looking for points that have a high mean. And this matches more or less the intuition of what I drew here, where we selected points that had a high mean but also a high variance. This was exactly the expression that they used. And now this term is essentially just a constant that would correspond to what is the best speed observed so far in our data set. Right? So capital X is our data set. And now we're looking for the data point x prime that we've already seen that has the highest speed so far. So that's just a constant. OK, so once you select a new x, then these are the parameters that you input to the robot. And then you carry out the experiment. You observe what is the speed. And then you can update the Gaussian process. So when I updated after observing a data point and redrew the curve, right, for the mean and plus and minus 1 standard deviation, implicitly it was done by using those equations. Okay, so the mean is revised in this fashion, and then the covariance function is revised based on that. Any questions regarding this? Yes?
Is there any expression for f? Like, how are you getting f of x new?
So your question is there?
Like, evaluate f of x new by observing speed of robot.
Yeah, so evaluate f of x new by observing speed of robot with parameters set to x new. So here, yeah, we don't know the function f. This is what we're trying to discover, right? But then what we get to observe is the output of that function. So that's what this means. Yeah. Okay, so the researchers at the time did some experiments where here you'll notice on the x-axis the number of observations that corresponds to the number of data points. So they would carry out experiments, observe the speed, one trial at a time, and then they did that up to 300 observations. As you can imagine, doing this 300 times took quite a while. Okay, and here we're not going to get millions of data points, right? So this is really just hundreds of data points. Okay, so then these curves, they essentially show what is the best speed that was discovered by trying different settings for different algorithms. Okay, the first two here are the Gaussian process, but then with different variances. So here 0.06 and here 0.6. And then they obtained a very good speed very quickly. So they perform quite well. In contrast, here we've got a hill climbing technique that's in red. And then the last one is just taking, selecting x's at random. So that did not do well at all because we're just trying things at random. And then we're just relying on luck. So yeah, so then it was fastest to use a Gaussian process. And then in that case, they use a Gaussian kernel. Any questions regarding this application? Yeah?
Is the intuition with the covariance doing better that you're kind of more experimental, you're willing to try out a larger space around your initial function? So 0.6 does a little bit better than 0.06?
Yeah, for the Gaussian process, yeah, 0.6. So yeah, that means there's higher variance. let me see. Okay, so we have to check again in the paper what exactly this is the variance of. It might be, yeah, so I'm not sure. I'm not sure if this is the variance that's part of the prior or something else, but in any case, I guess with more variance, there's something that they allow to just have more uncertainty, and that tended to perform better. Oh, actually, no, sorry. I think this corresponds to this parameter right here for the kernel. Yes. Okay, so then what this would mean is that if this parameter is higher, then you have a covariance function that is greater. Okay, so if it is greater, it means that in this case, the curves are going to be more continuous. Okay. Any other questions? All right. Okay, so let's move on to the next set of slides.